Here we have a hoop, a wheel with spokes, and a disc that all have identical masses and radii. They're placed on the top of a 3-meter incline that makes a 20-degree angle with the horizontal. They're released and rolled from rest to the end of the incline without slipping. We want to rank these three objects according to the amount of time they will take to reach the end of the incline. To do this, we have to realize that the moment of inertia for the hoop is the biggest, so I'll put a 3 for the biggest. And for the disc is the smallest, and for the wheel with spokes is somewhere in the middle. And the reason is that the moment of inertia does not only depend on the mass, which is equal for all of them, but depends on how the mass is positioned. The further out it is from the center, the greater the moment of inertia. So for the hoop, all of the mass is far from the center, and that's why it has the greatest moment of inertia, whereas the disc is more uniformly spread out, and that's why it has the least moment of inertia. Now, the moment of inertia is like the resistance to rotation. So if it resists rotation more, it will take longer to get to the bottom of the incline. And so the hoop will take the most time to get to the bottom. The wheel with spokes will take the second most amount of time, and the disc will take the least amount of time. Next, we want to draw the free body diagram. But this time we want to be careful to draw the forces from where they act on the ball. So the force of gravity is always going to act from the center of mass and pull straight down towards the center of the earth. But the normal force, which is the ramp pushing back on the ball, is going to start from the point of contact between the ball and the ramp and come like this. So here we have Fn, here we have Fg, and the last force is the force of friction between the ball and the ramp, and so we'll start that from the point of contact as well. Next, we're asked to identify which of these forces provide a non-zero torque. So Fn provides a torque of 0 newtons, because if we look at, we have to remember that torque is R, F, sine theta. So R is the vector from the center of mass to where the force acts. That's our R for the normal force. And Fn is exactly in the opposite direction. And so theta here is 180 degrees, and the sine of 180 degrees is 0, and that's why the normal force doesn't provide any torque. The force of gravity also provides no torque. This should be Newton meters, by the way. And the reason the force of gravity provides no torque is that the force of gravity is acting right from that rotation point. And so in that case, R is equal to 0. And if R is equal to 0, we know the torque is going to be equal to 0. So the last one to think about is the force of friction. That does provide torque. So it's a non-zero torque, and the reason is that it is a force that acts at a distance from the rotation point. That force is perpendicular to the moment arm, and so it does provide a torque. So here we're to find the acceleration of the disc as it rolls down the incline. I think there'll be two important formulas. The first is I'm going to write the sum of the forces in the x direction. Going down the incline, I have the parallel force of gravity, and going up the incline, I have the force of friction, and that should equal to ma. And so the parallel component of gravity is mg sine theta. We don't know the force of friction, equals ma. If I look at my given information, I see I do have the mass, and I know g, and I know theta is 20 degrees, but I don't know the force of friction, and I don't know the acceleration. So I'm definitely going to need a second formula, and we'll use the torque formula. The torque formula, remember, the only force that's providing a torque is the force of friction, and that's going to equal to I alpha. I might be able to find the force of friction in this problem, but I have to figure out what alpha is. I can rewrite this as A over R, and that way I just have two variables. I don't know my force of friction, and I don't know my acceleration. But if I have two unknowns and two equations, I should be in good shape. So the force of friction is going to equal to IA over r squared. I know my moment of inertia is 0.02 kilograms meters squared. And I know my radius is 0.2 meters. And I have to square that. And so the force of friction turns out to be equal to 0.5 times the acceleration. I'll plug that into this formula over here, and I get 0.2 times 9.8 meters per second squared. I should put kilograms here. Sine 20 degrees minus 0.5 A equals 1.0 A. Units are important, don't forget them. Okay, so now we have 0.67 is equal to 1.5 A, and A turns out to equal 0.44 meters per second squared. Lastly, we're asked to solve for the speed of the disk at the end of the ramp. So what we know already is that the acceleration of the disk is 0.44 meters per second squared. The distance it rolls along the incline is 3 meters. Its initial velocity is 0, it starts from rest, and we want to find the final velocity. So I chose to use the formula Vf squared equals Vi squared plus 2AD. The initial is 0, so we have 2.44 meters per second squared, 3 meters, and so Vf is going to equal to 1.6 meters per second.